Once we have a PyTorch model defined, how do we train it and how do we actually use it to get predictions on data points we've never seen before? That's what we're going to cover in this video. So let's say you have written a class, right? In this case, it is a model that recognizes images of handwritten digits. And you've written your constructor. This right here is where you define your model architecture. And then you have your forward method. This is where we get the model prediction. But in this video, we're going to go over how to actually train a model in PyTorch. How do you call the right functions to do gradient descent? And you won't have to take any derivatives by hand. PyTorch will do all of that for you. But how do you actually, over some number of iterations, update this model and make it better and better based on the training data? We're going to explain the training loop in this video, and this is super fundamental to all future neural networks that you train. So the below code is going to be the same regardless of the neural network, and it essentially might seem like boilerplate code, but there's actually a lot of important concepts embedded within this. So the first step is to make an instance of your model, the class that we defined earlier. Next, you'll need to define your loss function. For our previous linear regression problems, we used the mean squared error. And it was kind of an ugly looking formula with a summation and a square, but we did kind of make sense of it. And ultimately, we realized that if we minimize that error, then we increase the chance that the model will do well on data points it's never seen before. Because this problem is a bit different. It's not a regression problem. It's a classification problem, right? Our model is taking in an image, and the model needs to predict which digit it is, and there's only 10 possible digits. So the model will actually output probabilities that the given input image belongs to a certain class. So given, say, a picture of a number 7, this model will hopefully output something like 95% for the class number 7. So the model is actually outputting probabilities here. And that's why we're not going to use the mean squared error whenever we are doing these probability-based models. The model is outputting probabilities. In that case, we will use something called cross entropy loss. And it sounds like an ugly term. And if you look it up, there's kind of a confusing math formula which isn't super important to understand, and we'll definitely go over that in a different video. But the fundamental idea here is because our model is no longer outputting continuous numbers, like if we were, say, predicting the price of an Uber or predicting how tall someone's going to be. Instead, our model is trying to do a classification here. It's trying to group the input. It's trying to put it into one of some fixed number of buckets. We're outputting probabilities here. And that's why we have to use a different error function or a different loss function. And this cross entropy loss, if we kind of skip down here, the cross entropy loss takes two things, just like the other error functions, the model prediction and what the actual answers are, the ground truth labels from our data set. So let's say model prediction is some sort of probability, and let's say that probability that we gave for some input image was 0.8, right? There was some 80% chance that the model thinks that that image of some number 7 is actually the number 7, right? Then in labels, right? Actually, labels is always essentially either ones or zeros, right? Label in that case would just be 1. The true answer is that there's 100% probability that that given image, let's say it was a number 7, belongs to the class of images of number 7. So just to kind of treat this loss function as a black box, it takes in probabilities of the model's predictions and the true answers and outputs our error. The next really important line of code that will appear in every single training loop is something called the optimizer. And this is essentially an object in PyTorch that does gradient descent for us. When we create the object, we need to pass in the parameters of the model.parameters. And model.parameters is going to tell this optimizer all the weights, all the W's inside this neural network that we need to optimize and update over some number of iterations of training. And you might be wondering what Atom is. Atom is kind of like gradient descent on steroids. It's an optimized, it's still doing gradient descent. It's taking those derivatives, it's using the learning rate. It's actually using a default learning rate. We didn't pass that in. It'll assume a default learning rate of 10 to the negative 3 or 0.001. But Atom is gradient descent with kind of some optimization tricks to dynamically change the learning rate across the course of the algorithm. Once we get closer to the answer, right? We are getting closer to the minimum of a function, we don't want to accidentally overshoot, right? We'd want to decrease the learning rate at that point. So that's an example of some of the tricks and optimizations that Atom uses, but torch.optim.atom is still gradient descent. Next, we always have to define the number of epochs. An epoch is actually defined as the model being trained on the entire training dataset once. So 5 epochs would be 5 passes over the training dataset. You can kind of guess that as you do more epochs, the model, quote unquote, would memorize the training data better and better. Too many epochs, of course, might not be good, as we want our model to not, pay attention to small, unnecessary details in the training data. And that's essentially called overfitting. And we want the model to perform well on data it's never seen before, rather than solely memorizing the training data. Then we will essentially iterate over the number of epochs. And we have something here called a train data loader. That's just a couple lines of code to define. And I've already done that for us earlier in the code. We can kind of delve into the couple lines of code needed to create the train data loader in a different video. But essentially, this is an iterator that is giving us tuples. And it's giving us a batch of images, right? So images is a batch of images where each image is 28 by 28, or you can think of it as 784. And we have the corresponding labels, or what digit that is in the image for each of those images. So images and labels are the same size, and we're kind of pairing them up in a tuple. The first thing we have to do with the batch of images is, instead of having it be 28 by 28, if we kind of refer back to the model architecture here, we notice that the first linear layer is expecting essentially a vector of size 784. So we're essentially just flattening out, we're viewing or reshaping. You could use torch.reshape here as well. You're essentially reshaping that image into a flat vector of size 784, but it's still encoding the same, information for every pixel in the image. The next part is the training body. These several lines of code right here are incredibly important to understand, are actually the main focus of this video. The first thing we'll do is we will call the forward method of our model. This syntax over here calls the forward method from the model class we define and essentially gets our model prediction. The next step we have to do is a bit of a frustrating line that is even required in PyTorch, but will essentially become second nature to you. Optimizer.zeroGrad cancels out all the derivatives that were calculated from the previous iteration of gradient descent. We know that at every iteration, we want to recalculate the derivatives so we can update our weights, right? But PyTorch by default will store the previous derivatives, and if it'll still use them and add them up with the derivatives we calculate for this iteration of gradient descent, unless we say ZeroGrad, which cancels out the gradients from the previous iteration. Next, this is a line of code that will always appear in a training loop. It is calculating the loss or the error based on our current model prediction. That is one parameter passed into the loss function, as well as the ground truth labels. The next step is probably, or the next line of code is probably the most important line of a training loop in PyTorch. Loss.backward. This will calculate every single derivative necessary to perform gradient descent. This model, depending on how big the neural network is, may have tons of W's, tons of weights, and tons of derivatives that need to be calculated, specifically the derivative of our error with respect to those weights, so then we can update those weights based on the learning rate. But so loss.backward is essentially probably the most computationally intensive step of this entire program. It is calculating all necessary derivatives and storing those in such a way that we can actually use them. For the next line of code, optimizer.step, this is the line of code that updates all of our weights. So you can think of optimizer.step as doing new W equals the old W minus the derivative times the learning rate. This is exactly what optimizer.step is doing. It is taking a step in the direction, hopefully towards the minimum of our loss function. The whole point of gradient descent is minimization, and it is using all the derivatives that we calculated in the previous step or the previous line of code. And then we can actually see how the model is actually doing once training is done. So I've actually gone ahead and ran this cell, right? We have a trained model now. It has the right weights in this model object that was updated over the course of this algorithm. And if you're wondering, just a reminder as to how we actually updated the weights, it's because for our optimizer, which actually does the step, we told the optimizer at construction time which model, the parameters of the model to update. So after this line of code is done, we have the right model parameters. We can put the model in something called evaluation mode, which tells PyTorch that because we're just trying to get a bunch of model predictions, don't worry about calculating the derivatives for training. And then we can iterate over our test data loader, reshape our images as we did before, pass them in to the model, right? And then think about what the model prediction should be. it's going to be something like batch size by 10. We are feeding in a batch of images to the model in this line of code right here. And for every image, we are predicting a bunch of probabilities, specifically 10 different probabilities for every image. The probability that the image belongs to, say, the class of handwritten zeros or handwritten ones, all the way through handwritten nines. So you have 10 numbers for every single input image. But the way we can actually say what the model prediction is based on those probabilities is just by taking the max, right? Depending on which probability that was highest, we can say, okay, we'll take as what the model actually predicted. So if this is batch size by 10, we want to get the max index from every single row in this batch size by 10 tensor. So we will take max across dim equals 1. And then let's iterate over the images that we actually fed in for testing, print them. So we have to reshape them back into 28 by 28. And let's actually print the model prediction and see how the model did. So after we run this line of code, let's see how the model was doing. This was a im7 passed in, and it looks like the model, after we printed on index.i.item, actually predicted that this was a 7. So the model recognized this image. We can see the model did a great job here again. Predicted 2 as the highest probability, a 1 here, a 0 here, a 4 here, and the model did actually well for these 5 images. If we print some more, we can probably see that the model may have not done so great. So why don't we take a look at some where the model maybe didn't do so great. So here we have an image where the model actually predicted that this clear 2 was a 3. That was the highest probability it assigned among all the possible digits for this input. So this neural network is not perfect. It doesn't have 100% accuracy, but it's still pretty simple and achieves overall pretty good results without a convolutional neural network. Don't worry if you don't know what those are yet. But essentially with this simple neural network architecture, you can achieve around a 98 or 99% accuracy on this handwritten digit dataset. So that just shows that even with these simple neural networks, we're able to learn pretty powerful relationships we're teaching computers to see. So the main takeaway from this video is that our neural networks are going to get more and more complicated, but that training loop, that training block of code where we get the model prediction, we zero out the previous gradients, we calculate the derivatives, and we do optimizer.step. And of course, first we define our loss function, we define the optimizer. That is going to hold standard for almost every neural network we train. So be sure to check out the quiz to make sure you understand that.